Hi guys, we're going to go ahead and move on to Chapter 7, Section 5, and we're going to study something that are called inverse functions. Now, inverse functions are directly related to something that we have talked about in the past, which is called a relation. A relation is any pairing of an input and output, meaning you have x's and y's. So examples of a relation would be any ordered pair. So let's say I have 2, 1, or I have 3, -4. Okay, you can also show a relation as a table. Let's say I have a table. The reason why it's a relation is because you have inputs and outputs. I could have 0, -2, and 1, 4. Okay, so that's what a relation is. We are going to go ahead and talk about what an inverse relation is. Inverse relation means that the domain and the range are interchanged. So another little review for you. Remember the domain, those are the x values. So the domain of these two ordered pairs, your domain is 2 and 3. Your range is your y value, which is 1 and -4. Here, your domain are the x's, so 0, 1. Your range are the y values, -2, 4. What they're telling us for an inverse relation is that your domain and range have to be interchanged. That means that you just simply switch your x's and your y's. So 2, 1 switches and becomes 1, 2. Your 3, -4 switches to become -4, 3. If we are looking at this table, same thing. Your domain and your ranges switch. So 0, -2 becomes -2, 0. 1, 4 becomes 4, 1. Okay, now graphically, what would this even look like? The graph of an inverse function is a reflection. And what it reflects off is the line that is called y equals x. In order to find that line, you have to think, okay, the x and the y values have to match. So if x is y, 0 is y. If x is 1, y is 1. If x is 2, y is 2, going negative. If x is -2, y is -2. So you get a diagonal line that is right through the origin. Now, when you graph inverses, what should happen is you should get a reflection or a mirror image over this line. So let's go ahead and even look at these two. If I graph 0, -2, stay at 0, go down 2. Okay, now if I graph -2, 0, I go to the left 2, I don't go up or down. It just flipped over that line. Here, if I have 1, 4, goes to the right 1, up 4. Here, I go to the right 4, up 1. It just flipped over that line. So just a basic again, in order to have a relation, you need x's and y's. And inverse, you switch your domain and range, which just mean you switch your x's and your y's around. Graphically, what it looks like is if you graph the original relation and then you find its inverse, it's a reflection or a mirror image over the diagonal line y equals x. Now, our goal today is to verify that two functions are inverses. So what that means is they're going to give us two functions and say verify that they are inverses. The way that you do verification is you look at composition of functions. And we did this last week. So remember, this means you take the f function, where the variable is you plug the g function in. When you simplify it, all that should remain is an x. Now notice it says and. You can't just go one way. Now we have to flip it around. You take the g function, where the variable is put in the f function, you still have to only get an x. If that happens, then yes, those two functions are inverses of one another. If you find their ordered pairs, they're going to be just switching the x's and the y's from one function to the other. If you graph it, one would be, you'd go ahead graph, what would happen is the second one would be a reflection over that line. So today our goal is simply just to do the verification process. I have 4 examples for you, and then you can go ahead and try some on your own. Okay, so if I want to verify that f of x, where my function is x plus 3, I want to verify that it's an inverse function of x minus 3. So again, you have to verify using two compositions. So if I take the f function, where x is, I know I'm going to fill something in, but I still have my plus 3. What I'm filling in is g of x. Now when I go to simplify it, negative 3, positive 3, those are like terms. When I add them together, I get a 0, so it's just x. So it worked one way, but you can't say that it's an inverse unless it works both ways. So g of f of x. So the g function, that's where x is, minus 3. What I'm doing is where the x is, I'm filling in f of x. So x plus 3 goes in that location. To simplify it, I can combine like terms. Positive 3, negative 3, you get a 0. All you have left is x. So you just verified that yes, these two functions are inverses. This is what your assignment's going to look like today. You're going to do a composition where you put the g function into the f, simplify it, and make sure it's just an x. Then you go the other way. You take the g function, fill in the f of x function, simplify it, make sure that you just get an x. If they're both x, you did your job of verifying that they're inverses. Okay, we're going to look at 3 more. So if I have f of g of x, so I'm taking the f function, 4. Where the x is, I have to fill something else in. What I'm filling in is the whole g of x function. So 1/4 x minus 1/2. Now this one looks a little bit tougher, but it's not so bad. If you go ahead and you distribute, 1/4 of 4 is 1. If you have 4 and you're dividing it up by 4 people, everybody will get 1. So this would be 1x minus 1/2 of 4. Well, 1/2 of 4 is 2. There's a plus 2 on the outside. Minus 2, positive 2 cancels. So all you have left is an x. Your 2's canceled, x is what remains. Now you have to be able to go the other way. Take the g function. So it's 1/4. Where x is, that's where I have to fill something in, minus 1/2. Where x is, I'm filling in 4x plus 2, because I'm putting the whole f function in that location. Again, distribute. 1/4 of 4x is just 1x. 1/4 of 2. Now here you have to realize you are multiplying fractions. When you multiply fractions, it's top times top, bottom times bottom. So 2 times 1 is 2, over 4 times 1 is 4. 2 over 4 gives us 1/2. On the outside, I have a minus 1/2. Positive 1/2, negative 1/2 cancels. All I have left is x. You just verified that these two functions are inverses of one another. Okay, here is the next one. They're telling us that f of x is x squared. G of x is the square root of x. So if I find f of g of x, that means I'm taking the f function, and wherever x is, I have to fill something in, but the power 2 will remain. The x becomes the square root of x. Now remember from our last couple sections, a square cancels a square root. So this would cancel, but it never changes what's underneath. So that would just end up being an x. So that one was pretty darn quick. Now we have to go the other way. Take the g function and fill in f of x. So it's the square root, but instead of an x, I'm going to put an x squared. Well, guys, same idea. Square root cancels a square. It does not change the x. All I'd have left is the x. Now this last one, this is kind of like a challenge question. This is as hard as it will get. Same idea, okay? We have f of g of x. So the first thing I'm going to do is I take the f function, it's 8. I know I have to fill in something for x. It's to the power 3 plus 6. What's going in for x is a cubic root of x minus 6 over 2. Okay, if I look at my order of operations, I know exponents have to go first. I have an exponent outside of a fraction. So thinking back a couple weeks ago when we talked about properties of exponents, this exponent goes to the top and the bottom. So I have the 8 out front because you always do exponents before you would multiply. A cube cancels a cubic root. Because remember, if your exponent has the same number or the same value as the index, it would cancel. So this would cancel this. It does not change what's underneath. So the top would be x minus 6. The bottom, 2 to the power of 3. 2 times 2 times 2 is 8 plus 6. Okay, so property of exponents. The exponent goes to the top and the bottom. On the top, it canceled the cubic root because it was a cube. It doesn't change what's underneath. The bottom, 2 to the power of 3, means 2 times 2 times 2. It's an 8. Now, whenever you multiply something by a denominator, remember it cancels. My denominator is 8. I'm multiplying by an 8. They would cancel one another. So what I have left is the numerator, x minus 6. On the outside, I have a plus 6. Well, minus 6 plus 6 cancels. It's an x. And guys, that's about as hard as it's going to get. Yes, I know it's a little bit tricky, but you have all these skills, just putting them together. This is not enough to say it's an inverse yet. We have to go the other way. So take the g function. So I have a cubic root of x minus 6 over 2. Now where the x is, I am filling in 8x cubed plus 6. That's where the x was. It was before the minus 6, so I filled the f of x function there. Right away, I notice I can simplify. Underneath the radical, I have a plus 6 and a minus 6. So they would actually have a value of 0, leaving this as my problem. Now, again, last chapter. If I have a cubic root of 8x cubed, if you can take 3 of something out, you can go ahead and simplify it. 8 is 2 times 4. 4 is 2 times 2. X cubed means 3 x's. So I can cross off 1, 2, 3, 2, so that allows me to write a 2. I can cross off 3 x's, that allows me to write an x. So going back a couple weeks, if this is a cubic root of 8x cubed, by being able to cross off sets of 3, I can rewrite that as 2x. The bottom is a 2. 2 over 2 cancels, and I'd have an x remaining. Again, guys, this is a challenge question. This is as difficult as it will get. The basics of the idea were covered in 1 through 3. We will continue to work on inverses tomorrow. I hope you had a good time during our Algebra 2 section today. I hope you guys are all doing well. Please know that I'm thinking of you often and I miss you so very much. I'll talk to you soon. Bye.